What is going on, guys? Welcome back. In this video today we're going to learn about transfer learning and how we can take already pre-trained models as the basis for our new models. So let us get right into it. Alright, so we're going to learn how to do transfer learning in Python today, and we're going to do that in Tensorflow, which is a deep learning framework, so a framework that allows us to do machine learning with neural networks in a somewhat simple way. And the idea of transfer learning is to take a model that has already been trained on data for a specific task and to reuse that model or parts of that model for a different task, for a similar task. So I'm going to use my paint here to show you the basic idea visually. Now let's say we have some neural network. We have some input neurons, many of them, and then we have some hidden layers with some neurons in them, again, many of them. And then we have some output, for example. And of course we can have convolutional layers, we can have pooling layers, we can have recurrent layers, all sorts of layers that we can use here. And they are connected in some way. So I'm not going to go into the specifics here. This is just a very basic example here of some neural network. The important thing is that you have inputs, you have some stuff in between, and you have outputs. So let's say this is a neural network that gets as input some pixels. So this is an image that we feed into the neural network. Here we get some pixels, and the result is going to be whether the image shows a cat or a dog. And the result is going to be, let's say we use the softmax function, so we have percentages saying it's 0.7 cat and 0.3 dog. So 70% confidence that it's a cat, 30% confidence it's a dog. That's the basic neural network that we have. Now, training this neural network on images, on labeled images of cats and dogs will adjust these weights and biases here. So the weights of the connections between the individual neurons and the biases of the individual neurons and all the different things that you can adjust in the different types of layers and the different types of neurons. Again, very abstract example here. So whatever is in there will be adjusted in some way. So when you do that on a new model, what happens is you have some randomly initialized weights, biases, and other parameters. So you have just some random numbers, and as you train the model, these numbers are adjusted in a way that maximizes performance. Now, this video is not for complete beginners when it comes to machine learning and deep learning. So if you don't know what it means to have a loss function, if you don't know what it means to use gradient descent or activation functions or biases or weights, this video is not for you. This is a little bit more advanced here. So if you're a complete beginner when it comes to neural networks, I would recommend watching some of my other deep learning videos. This is a little bit more advanced. So I'm going to just assume that you know what a bias is, what a weight is, what an activation function is, what backpropagation is, and stuff like that. But you know that when you train a neural network, you adjust these parameters so that the neural network performs well. But in the beginning, you initialize them randomly. Now, let's say I train this neural network with a pretty good performance. It has an accuracy of, let's say, 0.995%, or not percent, 0.995, so 99.5% accuracy when it comes to these predictions, so it performs quite well. Now, let's say I have another task now, and this could be I feed in some pixels, and the result is going to be a single neuron for the new neural network that I want to build. Now, this is independent now. This is a different use case, a different task. And I want to have an output neuron that gives me a number. So the number could be 0, the number could be 5, the number could be 100. And let's say the neural network shall predict how many, or shall tell me how many cats or how many dogs, let's say how many dogs are in the image. So I get an image, I get the pixels, and I want to know how many dogs are in that image. And I could say 5, I could say 10, whatever. And I want to train this model. Now, this is one example for transfer learning, because what we can do here is we can take, instead of now setting up an architecture that is again randomly initialized and has again to adjust all the values so that it maximizes the performance here, I can just reuse what I have here. I mean, those are the inputs, but I can reuse all the stuff that I have here in between, all the hidden layers, or at least some of them, to get already the weights and biases that have been optimized for a somewhat similar task. Because even though we're not classifying now whether the image has a cat or a dog in it, we have something that relates to cats and dogs and animals. We don't have, we don't detect stop signs in traffic. We have a quite similar use case. And the idea is that when you take the layers with the parameters that have been trained on something that relates to dogs and cats, there is some structure in there, some weights and biases in there that are useful for the task. So the idea is that when we reuse the layer, we're going to converge to a good solution faster when it comes to this similar problem here. So instead of initializing randomly and then adjusting the weights to get to a good model, we take weights that are already performing quite well for a similar task. We maybe pop out the output layer and maybe one layer before the output layer, and then we reuse these layers, we connect them to a new output neuron, and we train the model from here. Of course, we will need some adjustments, but the idea is that we're going to be closer to the optimal or to a good solution than when we start from scratch randomly. This is the idea of transfer learning, and this is what we're going to do today. Now, this is a very specific example, so it doesn't have to be a similar task. You could also have the cat-dog classifier, and then you want to use it to classify horses and deers, for example. Or you might have a car classifier, and you might want to use it for a truck classification. Or in general, you can say you have a neural network that classifies a different number of categories. So you have shoes, you have shirts, you have monitors, you have books and animals, for example. And because this model recognizes objects or animals or entities, you could take that and train this model to classify other entities, which is what we're going to do here today. So I'm going to do all of this in Python here with you, and we're going to use TensorFlow. I don't know if I mentioned it in the beginning. TensorFlow is a deep learning framework, so a framework that we can use for machine learning with neural networks. And of course, we need to install it. So we're going to say pip3 install, or just pip install in your command line TensorFlow, and we're also going to use NumPy. So install TensorFlow and NumPy, and then I'm going to work in a Jupyter notebook here today, just so that I don't have to run the full code every time I want to do something. And we're going to start with the imports here. So import NumPy SNP, and from TensorFlow.keras.datasets, we're going to import a dataset called the CIFAR 10 dataset. This is just a dataset where we have 10 different categories and images that are showing one of these 10 objects. So I think we have horses, I think we have deers, I think we have, I don't know exactly what the classes are. I think we have cars or something like that. So we have 10 different entities, and we're going to train a neural network to classify 8 of them, and then we're going to use that neural network or layers from that neural network to classify the other 2 that it doesn't know about before. So we're going to say also from TensorFlow.keras.models, we're going to import the sequential model. And then we're going to say from TensorFlow.keras.layers, and here we're going to import a convolutional 2D layer, so conv 2D. We're going to use max pooling 2D, a flatten layer, a dense layer, and a dropout layer. So in this video, I won't focus too much on the layers that we use. So this is not a neural network tutorial where I explain what a convolutional neural network is and what these layers do. I'm going to use them and show you just the transfer learning part. So we're not going to focus on neural network fundamentals here. So after the imports, we're going to get the data by saying xtrain and ytrain are going to be in one tuple here. And then we're going to have xtest, and I'm mistyping a little bit more frequently because I got a new keyboard with a new layout. So I'm using the US keyboard layout, even though I'm European, because it's just better for coding, but I need to get used to it. So xtrain, ytrain, and xtest, ytest in separate tuples are going to be equal to CIFAR10.load_data. And this is going to automatically do the train test split for us. So we're going to use the train data, we're going to use this to train the model, and we're going to use the test data to evaluate the model. Now we're going to split the classes we're going to reserve 2 classes for the transfer learning part, and those are going to be 8 and 9, whatever they are. I don't even know, to be honest. We're just going to use 8 out of 10 classes for the training, and we're going to then have a new use case, quote unquote, by training also a model on 8 and 9. So what we're going to do here is we're going to say mask underscore train underscore 8 is going to be equal to np numpy is in, so is it part of ytrain split classes invert equals true. So we're basically taking all the training data for the instances that are not 8 and 9. So we're going to train from 0 to 7. And we want to flatten this. And then we can do the same thing for testing. So we're going to say mask test 8 is in ytest split classes and flatten. So when we look at this, mask train 8 is going to give us true, false, false, and so on, telling us which of those are actually, which indices here. So index 1 is part of those that we want to use, and index 2 or index 0 is that we want to use. Index 1 and 2 are those that we don't want to use, or let me just see if it's that way or the other way around, just by using statistics here. Yeah, so we want to use all of those that are not 8 and 9, so we have a lot more trues, and we don't want to use the 8s and the 9s, so those are the false occurrences here in the training and in the testing data. So we're going to say now that the xtrain 8 data, so the training data that we want to use for the first model, and the ytrain 8 data is going to be equal to xtrain, and we're going to use those that are true in the mask train 8 object, and we're going to do the same thing for ytrain. So ytrain, and then mask train 8. And then we're going to copy this. We're going to do the same thing for test. So all we're doing here is we're splitting the data into instances where we have the classes 8 and 9, and where we don't have the classes 8 and 9, so that we can do these 2 different use cases here. So test and test and test and test. There you go. So now we have only a couple of the occurrences, most of the occurrences, or most of the data, but not the data where we have the classes 8 and 9. Or actually 9 and 10, but the indices are, or actually it's 8 and 9. So I'm not sure, by the way, if we can get somehow the labels. I think we should be able to do that. So maybe with a question mark. Cyfar 10. Do we have something like labels or classes? Let me just see. Cyfar 10 classes. I just want to know the labels. I think we have airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. So basically what we're doing is we're training on all of this, and then we're going to have a second model trained on those 2, so distinguishing between a ship and a truck, and we're going to use the model that was trained on those images to classify these 2. Yeah, so I don't know how to get the classes. I'm sure there is a way to get the classes from here directly, but I don't know what the attribute is. So now what we want to do is we want to do the same thing also for 2. So now we're going to get this, we're going to copy this, and we're going to also copy this here. And now we're going to do the opposite. So we're going to change 8 to 2. Actually, we can do that with a substitution. So we're going to say substitute 8 for 2. And we're going to say that we don't want to invert this time. So we want to have everything that is 8 or 9, and then we're going to define that the same way. I think that should be correct. Let's run this. There you go. And I think we should be able to see in the length difference. So if I go x underscore train underscore 2 length, is that the function? No. How do we do that in NumPy? Do we just say length? 10,000, and if I go with the 8, it's going to be 40,000, yeah. So now we have in this data set here, in this train and test data set here, in these two, we have the 8 and 9 classes, and here we have all the others. So here we have ships and what was it? Ships and trucks, and here we have all the rest. So what we're going to do now is we're going to, first of all, adjust the labels for the classification. So we're going to say y underscore train underscore 2 equals np is in, and then actually, what did I do here? Y underscore train 2, and then split classes. Yeah, I know why I'm doing this. The reason why we're doing this now is because we want to know, we don't want to have 8 and 9, we want to have 0 and 1. So either it is that class or not. So we're saying, is it part of that, which is just the first element, and then it's going to give us a 0 or a 1. So we want to have this as type int. And then I'm going to copy this, and I want to say test underscore 2, and here also test underscore 2. So I think that is why we're doing this here. Let me just see. Yeah, we have zeros and ones because we're now asking, is this class 8 or not? Instead of having 8 or 9. All right, so that's the pre-processing. Now we're going to build a model to train on the 8 classes here. So we're going to say model equals sequential, and we want to have a sequential model with the following layers. We're going to use square brackets to put in the layers here. And the layers are going to be, first of all, a convolutional 2D layer, 32, and the size is going to be 3 by 3. The activation function is going to be equal to ReLU, rectified linear unit. And the padding is going to be equal to same. And then the input shape, since this is the first layer, is going to be the shape of the data set, 32 by 32, 3 channels, RGB. So we have 32 pixels times 32 pixels with 3 colored channels. That is our first layer. This is our convolutional 2D layer. This layer is going to be followed by a max pooling layer, 2D. With the 2 by 2 size here. There you go. And then we're going to have a dropout layer for regularization, so 0.25. And then we're going to basically copy this. We're going to change a couple of things though, so we're going to change this to 64. And of course, we don't need an input shape since this is not an input layer. And we're going to use the same max pooling and dropout layer. Then we're going to flatten all this. And then we're going to put it into a dense layer with 512 neurons. And of course, you can adjust that. You don't have to use the same architecture that I'm using here, but we're just going to go with this for the video. And then we're going to use another dropout with 0.5. And then finally, we're going to have a dense output layer. This is important now. This layer needs to have 8 neurons because, of course, we have 8 classes that we predict. And the activation here is going to be softmax so that we have the probabilities for each class that all sum up to 1, so to 100%. So here we want to have softmax. That is the idea. Okay, so this is our model. We're going to train it now on the 8 classes. Where did I mess up something? Did I forget a comma somewhere? I actually didn't. Oh, yeah, here I have a comma missing. There you go. So now we defined the model. Now we need to train the model. But first of all, we need to compile the model. So model.compile. The optimizer is going to be the Atom optimizer. We're going to have a simple loss function that we use since we have multiple classes to predict. So sparse underscore categorical underscore cross entropy. And we're interested in the following metrics. Accuracy. Yeah, that's it. So this is the compilation of the model, and now we're going to fit the model. So we're going to say history, or actually we don't need a history. We're going to just say model fit, and we're going to fit it on, of course, x underscore train underscore 8, y underscore train underscore 8. Epochs, we're going to train it for 10 epochs. I'm going to skip this part when it's training because it will take some time here. And the validation data is going to just be the test data because why not? We just want to see how fast it gets to a decent performance here. So we're not interested in actually evaluating the model. We're interested in seeing how fast it approaches a good solution based on the validation data. So it's actually not testing data. It's more like validation data in our case here. X test 8, Y test 8. All right, so that's it. We're going to now train this. You can see it's training the model. It will take around 30 seconds per epoch, 10 epochs. I'm going to skip that part, and we're going to continue once the model is trained. Sorry guys, I just realized that I forgot an important step. After loading the data, we need to normalize it by dividing by 255, because what we load here are pixel values from 0 to 255, RGB values, and we want to have values from 0 to 1 for the neural network. This is going to increase our performance, improve our performance. And because of that, we're going to say here x underscore train equals x underscore train divided by 255. And the same thing is going to be done for the testing data, but of course only for the X data, because the Y data are the labels, the X data are the pixels, and this is what we want to normalize. So X train, X test, then we're going to restart the kernel and do everything from scratch here so that we make sure nothing is messed up. We're going to run all of this again, and this is going to then give us, hopefully, a better performance. As you can see, it already starts better. All right, so we're done with the training now. We got a validation accuracy of around 73.7%, so this is not too bad. And what we want to do now is we want to train a separate model. It's going to be the same structure, so I'm going to just copy that, but it's not going to have any of the weights or biases or parameters of this model. We're going to train a new model with the exact same structure on the two classes now. So we're going to say model2 equals this. Then we're going to say model2 compile. So we're going to do the same thing. Or actually, it's not going to have the exact same structure. We're going to change, of course, the output layer, because we now have a different structure. We're going to have one neuron in the end, and it's going to have the sigmoid function. Now, we could also have two with the softmax, but we're going to use now one with a sigmoid function. It's going to tell us if it's more of a ship or a truck, so 8 or 9. Or in our case, since we encoded this up here as 0 or 1, it's going to tell 0 or 1 as a sigmoid function. You can model this the way you like. I'm going to use it. I'm going to do it with a dense layer with one neuron and the sigmoid activation function. So this is going to be model 2. We're going to, I'm now compiling model 1 again. So model 2 is going to be compiled. And what we want to do now is we want to train this model on the two classes from scratch with random parameters at first, and then we want to see how much faster we approach a good solution when we use transfer learning by reusing this model instead of training it from scratch like here. So we're going to say model2.fit x underscore train underscore 2, y underscore train underscore 2. Epochs are going to be 10 again. And then the validation data that we're going to look at, validation data, is going to be x test underscore 2, y test underscore 2. I should have called this validation, not test, but it doesn't matter now. So I'm going to run this, and we have a problem. What is that? What did I mess up here? Of course, I'm using a loss function for a softmax layer. So we need to use a different loss function, of course, binary cross entropy, because now we have a dense layer with one neuron and the sigmoid activation function. So we use a binary cross entropy instead of a sparse categorical cross entropy. And you can see now it starts off with a good accuracy. It doesn't look too bad, but it has to figure out everything from scratch. Now, this is, to be fair, this is not the best example for transfer learning because we're going to get a quite good performance by just training on the data from scratch with randomly initialized weights, biases, parameters, and stuff like that. But we're going to see that the performance is going to approach a good solution faster when we use the layers that we already trained on the 8 classes here. And what we're going to do here while this is training, I'm going to explain what we're going to do. We're going to take this model that we trained on 8 classes, and we're going to freeze certain layers. Now, freezing layers means we're going to make them untrainable. So we're going to take parts of the model, we're going to freeze them, we're going to say, okay, no matter what you learn, don't change anything about those layers. And then we're going to train the rest of the layers. So in our case, we're going to freeze the convolutional base here. We're going to freeze the first 4 layers. This is now an arbitrary choice I make. We're going to freeze those 4 layers here. We're going to make them not trainable. And we're going to train these layers here on the 2 classes. And we're going to swap this for, again, a dense output layer with 1 neuron and the sigmoid activation function. That is what we're going to do. And then we're going to see how fast we approach a good solution. So now the final solution, the final accuracy here is 94.85% roughly. And now we're going to do the following. We're going to say model.layers. So this is again our first model, not model 2, this one here. Layers, and then index 0 is going to have the attribute trainable set to false. I'm going to copy this, and we're going to do this for 1, 2, and 3. So we can take the layers of the model and we can index them. So we want to have this, 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 and this frozen, so not trainable, which is done by doing this. Then we're going to pop the last layer. So model pop is going to pop the dense output layer with 8 neurons in the softmax function. And we want to add now a new layer, which is going to be a dense layer with 1 neuron and an activation, which is equal to sigmoid. There you go. So we can hopefully look at the layers here. There you go. You can see we have a convolutional, pooling, regularization, dropout, conv2, pooling, dropout, flatten, dense, dropout, dense. So we have the same structure, but we popped one layer and we added a different one. We froze those 4 initial layers here. So those 4 here are now untrainable. So our training is going to happen on these layers here. And we're going to say again, model, actually I can copy this from up here. Model without a 2 here, model compile like this. And then I can also copy this from here. We're going to fit in the same way, but now with a different data. So again, this model here that we're modifying, popping, adding something to it, compiling, and fitting, this model has already been trained, but not on this data. We trained it on the 8 classes, and now we're using that model that has already been trained on the 8 classes. We modified it a little bit. We froze some layers. We removed a layer. We added a layer. Now we're training this model on X-train2 and Y-train2. And when I run this, you can see that this approach is a good solution in the first epoch already. So actually, this is not too different, is it? I mean, we have 90, 91. Oh, it is different. So we can see here we had an accuracy of 87.10, and here we have 91.75 already. So we approach a good solution earlier in the process, in the earlier epoch. So here's the first time in the 5th epoch we get 0.93. This is what we get here already in the 2nd epoch. I'm not sure if the final result will be better. We will have to see. Doesn't look like this. Okay, so in this case, the final result is not better. It's pretty much the same. But the idea of transfer learning is, and this is again a very simplistic example, but the idea is if you have a very complex machine learning model, a very large architecture, a very complex problem, it doesn't make sense to always train a model from scratch. Use models that have already been trained, free some layers, train the rest of the model, and then you can, first of all, approach a good solution faster. And even though it wasn't the case here necessarily, oftentimes you can also, since you're approaching a good solution faster, you can also optimize that good solution with fewer epochs, and you will end up with a better model sometimes with fewer epochs. But yeah, the goal of this video was to show you how to do transfer learning. So you have a model, you can also load it from a file, so you can export the model, you can load it, and then you can just take some of the trained layers, freeze them, and you can add some other layers, and you can modify the structure and all that, and then you can reuse that to not have to do everything from scratch. And especially when you get to very complex, very large tasks or large data sets that you have to train on, instead of doing all of this from scratch, you may benefit from reusing already trained models. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.